In module 20, we have already introduced the idea of confidence intervals, where we have discussed a method of determining confidence interval by using a pivot. Now, in the present lecture, we are going to discuss the idea of confidence sets as a generalization of confidence intervals. First, we shall discuss how one can obtain the confidence interval in case of discrete distributions. Then we discuss how one can obtain confidence interval by using the acceptance region of a test. Next, we will define the uniformly most accurate confidence interval, and we discuss the method of determining a uniformly most accurate confidence interval by using the acceptance region of the UMP test. Some examples are discussed in this connection. The idea of interval estimation can be extended to include simultaneous estimation of several parameters. For example, two parameters mu and sigma square of a normal mu sigma square distribution may be estimated by some region capital S, which is a subspace of the sample space script X. A 1 minus alpha % confidence region is a subset of the sample space such that if the samples were repeatedly drawn, then about 1 minus alpha % of these cases, this region will include the true value of the parameter. So, our discussion can be made somewhat more general if we speak in terms of confidence sets rather than confidence intervals. First, we shall introduce the idea of a confidence set. Let theta be the parameter of interest and script theta is the parameter space. Let capital X be the random vector with script X is the support of the distribution of X. Let p theta be the probability distribution of X. Now we define a confidence set. A family of subsets is capital Sx of script X is said to constitute a family of confidence sets for theta at confidence level 1 minus alpha if probability under theta belongs to capital Sx, this probability is greater than equals to 1 minus alpha. Now we discuss some special cases. Lower confidence interval. The lower confidence bound provides just a lower bound for the parameter of interest. That is, probability under theta greater than equals to some theta lower bar x is greater than equals to 1 minus alpha for all theta. Therefore, the confidence set is theta lower bar x to infinity and Sx equals to set of all theta such that theta bar x less than equals to theta. For example, if x1, x2, xn be a random sample from normal mu, 1 population, then x bar follows normal distribution with mean mu and standard deviation 1 by root n. Therefore, probability under mu root n into x bar minus mu less than equals to tau alpha is equals to 1 minus alpha, where tau alpha is the upper 100 into alpha % point of a normal 0-1 distribution. Hence, by interchanging sides we get probability under mu greater than equals to x bar minus tau alpha by root n is equals to 1 minus alpha. Therefore, x bar minus tau alpha by root n comma infinity is a 100 into 1 minus alpha percent confidence interval for mu. The upper confidence interval or the upper confidence bound provides just a upper bound for the parameter of interest, that is probability theta less than equal to theta bar x, theta upper bar x is greater than equals to 1 minus alpha, and therefore the confidence set is minus infinity to theta upper bar x, and Sx equals to set of all theta such that theta upper bar x greater than equals to theta. Next we define confidence interval. Confidence interval provides both upper and lower bound for the parameter of interest, that is probability under theta, theta lower bar x less than equal to theta greater than equals to theta upper bar x is greater than equals to 1 minus alpha. Therefore the confidence set is theta lower bar x to theta upper bar x, and Sx equals to set of all theta such that theta lower bar x less than equal to theta less than equal to theta upper bar x. Now we establish a relation between confidence set estimation and testing of hypothesis. There is a very strong correspondence between hypothesis testing and interval estimation. In fact, we can say in general that every confidence set corresponds to a test and vice versa. We next consider the method of test inversion and explore the relationship between a test of hypothesis for a parameter theta and confidence interval for theta. We consider the following result. Let for each theta naught belongs to script theta, capital A theta naught, which is a subset of the sample space script x, be the acceptance region of a level alpha test for testing h naught theta equals to theta naught. Then the set Sx, which is equals to set of all theta such that x belongs to capital A theta, is a confidence interval for theta at confidence level 1 minus alpha. We consider a proof of this result. Let capital R theta naught be the rejection region of the level alpha test mentioned above for testing h naught theta equals to theta naught. Now we know that capital A theta naught union capital R theta naught is equals to script x, the whole sample space. Now probability under theta naught x belongs to capital R theta naught is less than equals to alpha for all theta naught, or probability under theta x belongs to R theta is less than equal to alpha for all theta. Therefore probability under theta x belongs to A theta is greater than equals to 1 minus alpha for all theta, or probability under theta x or probability under theta theta belongs to Sx is greater than equals to 1 minus alpha for all theta. We consider the following example. Let x1, x2, xn be a random sample of size n from normal mu sigma square population. Suppose we are interested in the following testing of hypothesis h naught colon mu equals to mu naught versus h1 colon mu not equals to mu naught. We know that we reject h naught at level alpha if modulus of root n into x bar minus mu naught divided by s is greater than t alpha by 2 comma n minus 1. Therefore the rejection region of the test is R mu naught equals to set of all x such that modulus of root n into x bar minus mu naught by s greater than t alpha by 2 comma n minus 1, and therefore R mu is equals to set of all x such that modulus root n into x bar minus mu by s greater than t alpha by 2 comma n minus 1. Therefore A mu is equals to set of all x such that root n into x bar minus mu divided by s is less than equals to t alpha by 2 comma n minus 1. This is equivalent to set of all x such that mu belongs to Sx, where Sx equals to set of all mu such that x belongs to A mu. Hence A mu equals to set of all x such that x bar minus 1 by root n s by root n into t alpha by 2 comma n minus 1 less than equals to mu less than equals to x bar plus s by root n t alpha by 2 comma n minus 1, and hence sx equals to an interval which is x bar minus s by root n t alpha by 2 comma n minus 1 to x bar plus s by root n into t alpha by 2 comma n minus 1. Now we discuss the idea of confidence interval for discrete case. Let x1, x2, xn be a random sample of size n drawn from a discrete distribution with PMF px theta. To determine a 100 into 1 minus alpha % confidence interval for theta, we may use the distribution of the sufficient statistic capital T for theta. We consider the following result without proving it. For a proof of the result, one may see Casella and Berger's result. Let capital T be a discrete statistic with CDF. Capital F theta t is equals to probability under theta t less than equals to small t. Let alpha 1 and alpha 2 be two fixed real numbers such that alpha 1 plus alpha 2 is equals to alpha. Suppose that for each t, theta lower bar t and theta upper bar t is defined as follows. If capital F theta t is a decreasing function of theta for each t, then we define theta lower bar t and theta upper bar t by probability under theta lower bar t capital T less than equal to small t is equals to alpha 1, and probability under theta upper lower bar t capital T greater than equals to small t is equals to alpha by 2 is equals to alpha 2. If f theta t is a increasing function of theta for each t, then we define theta lower bar t and theta upper bar t by probability under theta upper bar t capital T greater than equal to small t is equals to alpha 1, and probability under theta lower bar t capital T less than equal to small t is equals to alpha 2. Then the interval theta lower bar t to theta upper bar t is a confidence interval for theta with confidence coefficient 1 minus alpha. We consider the following example. Let x1, x2, xn be a random sample of size n from Poisson theta population. Here capital T equals to summation xi is sufficient for theta. Since t follows Poisson n theta, the CDF of t is a decreasing function of theta. If capital T equal to small t is observed, taking alpha 1 equals to alpha 2 equals to alpha by 2, we have to solve theta lower bar and theta upper bar from the equations summation over I from 0 to t e to the power minus n into theta upper bar into n theta upper bar whole to the power t divided by t factorial is equals to alpha by 2, and summation over I from t to infinity e to the power minus n into theta lower bar into n theta lower bar to the power I by I factorial is equals to alpha by 2. Now we know that if x follows Poisson lambda, then for any non-negative integer k, probability x less than equals to k is equals to probability y greater than equal to 2 lambda, where y follows chi-square distribution with 2 into k plus 1 degrees of freedom. Hence we get probability chi-square 2 into t plus 1 greater than equal to 2n into theta upper bar is equals to alpha by 2, and hence theta upper bar is comes out to be 1 by 2n into chi-square 2 into t plus 1 into comma alpha by 2. Again probability chi-square 2t less than equal to 2n into theta lower bar is equals to alpha by 2, and therefore theta lower bar is equals to 1 by 2n into chi-square 2t comma 1 minus alpha by 2. Hence chi-square 2t comma 1 minus alpha by 2 divided by 2n comma chi-square 2 into t plus 1 comma alpha by 2 divided by 2n is a confidence interval for theta with confidence coefficient 1 minus alpha. Now we discuss a optimum property of confidence sets. Since there is a one-to-one correspondence between confidence sets and test of hypothesis, there is some correspondence between optimality of tests and optimality of confidence sets. Usually, test-related optimality properties of confidence sets do not directly relate to the size of the set, but rather to the probability of the set covering false values. The probability of covering false values or the probability of false coverage indirectly measures the size of the confidence set. Intuitively, smaller sets cover few values and hence are less likely to cover false values. An optimum property of confidence sets is given in the following definition. We now define uniformly most accurate confidence set, UMA. A family of confidence sets capital S naught X is said to constitute a family of UMA confidence sets at confidence level 1 minus alpha if probability under theta belongs to S naught is greater than equals to 1 minus alpha for all theta, and probability under theta dash belongs to S naught is less than equals to probability under theta dash belongs to S for all theta not equal to theta naught whenever S x satisfying 1. A 1 minus alpha confidence set that minimizes the probability of false coverage over a class of 1 minus alpha confidence sets is called a UMA set. UMA confidence sets are constructed by inverting the acceptance region of UMP test, as we will prove below. We consider the result. Let for each theta naught belongs to script theta, capital A naught theta naught be the acceptance region for a UMP level alpha test for testing H naught, theta equals to theta naught. Then the set S naught, which is the set of all theta such that X belongs to A naught, is UMA at confidence level 1 minus alpha. Let R naught theta naught be the rejection region for the UMP test mentioned above for every theta naught belongs to script theta. By the previous result, probability under theta belongs to Sx is greater than equals to 1 minus alpha for all theta. Therefore, probability under theta x belongs to R naught theta naught is greater than equals to probability under theta x belongs to R theta naught for all theta not equals to theta naught. Here R theta naught is the rejection region of any other test. This is due to the UMP property of the test, which implies that probability under theta x belongs to A naught theta naught is less than equals to probability under theta x belongs to A theta naught for all theta not equal to theta naught, where A theta naught is the acceptance region corresponding to R theta naught. Thus, probability under theta dash belongs to S naught is less than equals to probability under theta belongs to or theta dash belongs to Sx for all theta not equals to theta naught, and whatever Sx satisfying probability under theta belongs to Sx is greater than equals to 1 minus alpha. Now we consider some examples. Let x1, x2, xn be a random sample of size n from normal theta, 1 population. The rejection region for a UMP test of size alpha for testing H naught theta equals to theta naught versus H1 theta greater than theta naught is root n into x bar minus theta naught is greater than tau alpha, where tau alpha is the upper alpha percent point of a standard normal distribution. And we define the acceptance region capital A theta naught equals to set of all x such that x bar less than equals to theta naught plus tau alpha by root n, and therefore Sx equals to set of all x such that theta greater than equals to x bar minus tau alpha by root n. Hence, the UMA confidence interval of level 1 minus alpha is given by the interval x bar minus tau alpha by root n to infinity. Note that the more commonly used two-sided interval x bar minus tau alpha by 2 divided by root n comma x bar plus tau alpha by 2 divided by root n is not UMA, since it is obtained by inverting the acceptance region of a test H colon theta equals to theta naught against HA colon theta not equals to theta naught, for which no UMP test exists. We consider another example. Let x1, x2, xn be a random sample of size n from rectangular 0 theta population. The UMP test for testing h naught theta equals to theta naught versus h a theta not equal to theta naught is given by we reject h naught if x ordered n greater than theta naught or x ordered n less than theta naught into alpha to the power 1 by n, and therefore the acceptance region is defined by a theta naught equals to set of all x such that theta naught into alpha to the power 1 by n less than equals to x ordered n less than equal to theta naught, and thus Sx equals to set of all theta such that x ordered n less than equal to theta naught less than equals to x ordered n divided by alpha to the power 1 by n. Hence, the UMA confidence interval of level 1 minus alpha is given by x ordered n comma x ordered n divided by alpha to the power 1 by n. In this lecture, we have seen that the uniformly most accurate confidence interval can be easily obtained from the acceptance region of the UMP test by inverting the acceptance region. As we have seen that in case of normal distribution with mean theta and variance 1, the traditional confidence interval for theta, that is x bar minus tau alpha by 2 by root n comma x bar plus tau alpha by 2 divided by root n, is not the UMA confidence interval, because it is based on a test which is not uniformly most powerful. We have also seen that in case of discrete distribution, the CDF plays a very vital role in determining the confidence interval for the parameter.